Hello and welcome to this lecture. We're going to deal with two topics in this lecture. These are closely associated with inner products and they sort of tie up with subspaces and all these other things that we've been studying so far. So these are one is linear functional. It's actually a special case of a linear map and it has a very interesting and simple connection to inner products. So that's something that we will see. And the other one is orthogonal complements. Once again, you might be familiar from what you've studied earlier about this in description of planes in R3, right? So you can describe a plane either by providing two vectors on that plane, or you can provide a vector that is normal to the plane, right? So this normal description of a plane is something that you might have studied. So orthogonal complement is sort of related to that. So what is this orthogonal complement? And inner product, of course, plays a big role in that as well. So these two we'll study in this lecture. Okay, so let's get started. Quick recap: we've been looking as usual at vector spaces over a scalar field, real or complex. We've seen matrices are very useful to represent these linear maps and work with them. There's these nice results about dimension of null and space, null and range, and four fundamental subspaces and their relationship, how they are useful in solving linear equations. This whole invariant subspace, one-dimensional invariant subspace, leading to the definition of eigenvalues, eigenvectors, and how you can have an upper triangular matrix representation in a suitable basis for any linear map. That's something we've seen. We also saw that some linear maps are diagonal, so that's also something that's very interesting. And the latest topic we are studying this week is inner products and norms, and how orthogonality and orthonormal bases simplify a lot of descriptions, and we'll continue on in that mode today. So we'll see inner product orthogonality helps us in simplifying some of the notions and connections between these four fundamental subspaces and linear maps and all that. Okay, and we saw one very nice result that in fact in an inner product space, when you have a proper inner product defined in the vector space, you can have an orthonormal basis with respect to which any linear map, I should say it in reverse, for any linear map there exists an orthonormal basis such that the matrix representing that linear map in that basis becomes upper triangular. So that's very nice to know. It's good to have orthonormal basis because we know coordinates are easy to find and all that. Okay, so this is a quick recap. Let's study now two topics in this lecture: linear functionals and orthogonal complements, which further illustrate the usefulness of having this inner product. Okay, what are linear functionals? Linear functional is a linear map, except that the result of the linear functional is always a scalar. Okay, so it maps vector to scalar. That's called a functional. Okay, a functional is usually like that. You have a vector or a more complicated object. From that, if you do a function and you take yourself to a scalar, a very simple object, usually people call it a functional. So a linear functional is nothing but a linear map, except that from V you go to F, the scalar field itself, right? So that is called a linear functional. So all the properties we studied for linear maps apply for linear functionals as well, right? Except that the range is actually a scalar, so it's got dimension 1 or 0. So it's very simple in some sense. So maybe we can expect a simple description. Okay, so let's look at a few examples to get ourselves started. So if you look at linear map phi, so it's common to use a notation like phi as opposed to t for a linear functional. If you look at R3 to R, here's an example of a linear functional. You can see it's a linear map. It works out in some obvious way. So in fact, in general, if you go from Fn to F, any linear map would be like C1x1 to Cnx, and it's very easy to see. Linear maps correspond to matrices. The matrix of a linear functional is going to be a 1 by n matrix, right? So if you go from Fn to F, the matrix is a 1 by n matrix. So clearly, when the map itself is represented by something like this, right? So it has to be like that. Okay, all linear functionals will be in this form. It's quite easy to see. But maybe potentially, if you look at a slightly different type of linear functional, which takes say polynomials of degree less than or equal to 2 to the real line. Okay, so here is a very interesting little definition where we use this integration, right? So we use, you take a polynomial of degree less than or equal to 2, and then you do integral from 0 to 1, p of x times cos pi x. Now this cos pi x is not a polynomial, right? It seems to be some other object, but overall this phi is still a linear functional. right? You can use any the definition for the linear map. You see the additivity works because integration is also linear, and scalar multiplication also works, right? But this cos pi x is a bit disturbing, right? It's not something that's part of my linear algebra, the field or the vector space that I'm dealing with here. It seems like something else, but nevertheless, the overall phi is a linear map. So can I say something in this case? So is it still that, is there still a simple description in terms of my own vector space, even if the function involved is cos or something else which is outside, okay? So things like this can happen sometimes. You may get a linear map from a vector space to the scalar field, but it may involve things outside of your vector space, okay? So something else may happen and it may look very strange and different to you, but I'm still in this vector space, right? So something simple must be there for describing such things, and it turns out that's also true. And once you have an inner product space, such things can be very, very clearly written down, okay? So here is a, so if your V is not just a vector space, it's an inner product space. There's a very interesting example of a linear functional. It's a very simple linear functional. I've spoken about this when I introduced inner product as something that connects inner product to the world of linear maps and linear algebra, right? So if you fix a particular vector u and define a phi as the inner product of v comma u, then you have a linear functional, right? So it's quite easy to see, all the properties can be verified directly. So this is a linear functional. It's a very interesting linear functional. The reason is, we can ask a very interesting question: can there be in a product space any other linear functional which is not like this, right? So this looks like a very typical or an easy example of a linear functional. Can there be a linear functional which is not like this, right? So that's an interesting question one can ask, and it turns out there is this wonderful result which is called Reyes' representation theorem, Reyes representation theorem as it's called. If you have a finite dimensional inner product space, and if somebody gives you a linear functional on V, could be whatever linear functional, it could involve the elements of your inner product space or maybe some other element like the previous example we saw, whatever it is, as long as it's a linear functional, it turns out there exists a unique vector in your V, in your own the inner product space that you started with, such that that linear functional becomes the inner product of V comma u. Okay. So in other words, this inner product of V comma u is the only linear functional that's interesting in a finite dimensional inner product space. So that's the Reyes representation theorem. It's probably intuitive, it's very easy to see, but let's write down a proof, and the proof involves orthonormality and the properties of inner product and all that. Okay. So you start with an orthonormal basis for V, okay, and then you see phi of V, right? Now once you have an orthonormal basis, any vector V in V can be written as V comma E1 E1 plus dot 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 V comma En En, right? So this is true. So this is orthonormal, so you can write like this. So this is what I have done here. So instead of V, you plug in this guy, V equals this, right? So instead of V, you put that in. Now you use the property of the linear functional, right? So phi is going to sort of go inside the linear combination. V comma E1 is a scalar, E1 is the vector, so phi will just apply on that E1, the scalar will come out, right? So this is a linear map, so it's under linear combinations, the phi will go in, right? So you have phi of E1, phi of En. Now notice this phi of Ei is a scalar, okay? Okay, in general complex, okay, it could be if it's real, but otherwise it's complex, right? So it's a scalar. Now what happens when an inner product is multiplied by scalar? That scalar can be taken inside, right? It could be taken inside either to the first argument, in which case it would just enter in without anything else, or it could be taken inside into the second argument, in which case it would be conjugated. Okay, so I forgot to put the bracket here, so this is important. Okay. So I am taking it into the second argument. That's the reason why I think the second argument is interesting here. So I am taking it into the second argument, so I have to conjugate, right? So I am putting a conjugate there, right? So this is so far so good. So you see how the orthogonality and the inner product are nicely playing to convert any linear map into a inner product like situation. Okay. So there is a bug here, I apologize for that. There is this actually, okay, so let me just write it properly. You should have a v comma phi of n here, right. So you can see how the same thing has been written here, and then I can combine all these guys, right. So that is what has been done, I think, in the way I wrote it. So this is for each term the phi goes in, and then I sum up all the remaining guys, right. So when I do that, I get that. Okay. So you can see that that works out quite okay. So hopefully you see that it's quite clear, I think. Okay. So that becomes the whole thing. So then once you do that, you use the additivity in the second argument. So this becomes inner product of v comma this. Okay. So I just showed you the intermediate step there. Each term phi goes in and becomes conjugate, and then you add up all of those. V is the same, so the second one becomes additive. So if you put u as this guy, right, whatever the second one is, phi of e1 bar e1 plus this, then phi of v becomes v comma u. Okay. So somebody gives you some linear functional phi of v, you can always go in and find the u such that that phi of v becomes inner product v comma u. Okay. So that's interesting. Though this statement also makes something about uniqueness of this vector u. I will leave that as an exercise. Go ahead and try and show. The book also has the proof for uniqueness. Usually uniqueness is always done by contradiction. You assume there are two different vectors u1 and u2, and then show finally that u1 has to be equal to u2. It's quite easy in this case. You can do that. Okay. So this is reassuring to know. So any linear functional in an inner product space which is finite dimensional, you will have only the inner product showing up. You can always find a u so that this will happen. Okay, so let's go and use it in our example that we had here. We had polynomials of degree less than or equal to 2, and we use this inner product. P comma q is integral 0 to 1 p of x q of x dx. And let's say we look at this linear functional which is defined with respect to this cos pi x showing up. This example is done in your book as well. You can take a look, but let me just quickly illustrate what's going on. So what does race tell you? Race tells you there exists a q of x which is a vector in your space. What are vectors in my space? These are polynomials of degree less than or equal to 2. There exists something such that this phi of x, which is integral 0 to 1 p of x cos pi x dx, has to be actually equal to integral 0 to 1 p of x q of x dx. So this is the main race result. Now the question is, how do you find this q of x? You use the elements from the proof. So you first find an orthonormal basis for this p2 of r. This needs a little bit of work. For instance, you could take 1x square, which is an obvious basis, and run Gram-Schmidt on it. Once you run Gram-Schmidt on it, you will get E0, E1, E2. E0 will be 1 itself. E1 will be a slightly modified version of x and 1, and then you will have x squared. Okay, so this can be done. You can find an orthonormal basis. Once you find an orthonormal basis, q of x is simply, just from the proof before, phi applied on the orthonormal basis. So that will involve an integration, right, with x cos x, x squared cos x like that. And then E0 itself. You evaluate this polynomial, you will get q. Okay. So this is the basic idea. I am not doing it in great detail. Your book has the details here if you want to see it, and that's true. Okay. So this is a nice result to see, right. So integral 0 to 1 p of x cos pi x, which is really not a polynomial, is actually the same as integral 0 to 1 p of x, a polynomial of degree 2. In this case, it will be equal to 2 as well. Okay. So that's the example worked out. And that's a summary of linear functionals. I don't want to say too much more about linear functionals. There's nothing more to say, right? Once you have the race representation theorem, it is simply the inner product. Okay, so all these inner products together make linear functionals. We'll come back and look at these things later on when we talk about adjoints and those definitions. This will be very interesting to look at as well. Okay, good. So let's move on to the next topic of this lecture, which is orthogonal complement. Okay, so it's very interesting to see how orthogonality and inner products can be used to define interesting subspaces of a vector space. Okay. So we have a vector space V, which is an inner product space, okay, and we consider a subset of that vector space, which is some u. I'll show you a simple example. U could be a point, you could be a set of points, you could be a subspace itself, you could be the entire V. Okay, so any subset. The orthogonal complement of u, we will denote it as u perp this perpendicular symbol is usually abbreviated and pronounced as perp. So, this is U perp is the set of vectors which is orthogonal to every vector in the subset U. Okay. So, that is the definition, it is written down in set theoretic notation below. U perp is the set of all V in the vector space V such that the inner product V comma U equals 0 for every U in U. Okay. So, for everything it has to be true, not just any one. Okay. So, that is important. That is definition, it is easy enough to see the definition. So, let us see a few examples and we will use our familiar R2. First is U equals 0. Okay. Supposing I take only the 0 vector in R2, what would be U perp? Okay. So, I will go through and write down all the 4 and then explain how this would go. Okay. So, you can see for U is 0, it is quite easy to see U perp, any vector is going to be orthogonal to 0, right. So, U perp would be the entire vector space. What if U is x1, y1, where maybe x1, y1 is not 0, right. So, what if U is x1, y1, what would be U perp? Okay. So, if you think about it, you are going to write U perp as the set of all V equals, let us say xy, such that the inner product of V comma U. So, U is just one point, right. So, this is for every U, but there is only one point in U. So, this would be x1 plus y1 equals 0. Okay. What is this? What is this description? This is a line through the origin, isn't it? This is a line through origin and it is perpendicular to the line joining x1, y1. So, if you were to draw this point and you have, let us say, x1, y1 here, U perp is you draw this line through this, then U perp would be the perpendicular line. Okay. So, this would be 90 degrees and this guy would be U perp, isn't it? So, that is nice enough to see. Okay. So, you take one point and ask which is the set of all one vector and ask which is the set of all vectors which is orthogonal, they will lie on the perpendicular line, it is easy to see. What if U itself is a line through the origin? The same example extends, right. So, this dotted line would be a line through the origin and then U perp would again be a vector which is perpendicular to it, right. So, because a line through the origin, there is only really one vector in it, right, it is one dimensional. So, there is nothing more to worry about. So, you just make sure it is perpendicular to that, it will be perpendicular to the whole thing. Okay. So, what if you take 2 points? Okay. So, here there are 2 cases, these 2 points could lie on a line through the origin. If they lie on a line through the origin, the same line through the origin, then U perp will be the line perpendicular to it. But in case they do not, in case x1, y1, x2, y2 are linearly independent, then what will happen? So, if linearly independent, then U perp is only 0, right. So, there is nothing else that will be orthogonal to both this and this, right. So, think about why that is true. So, if you have there cannot be one vector which is orthogonal to both of these guys. So, that would be you can write it down. So, supposing you say x1, y1, x2, y2, U perp is the set of all xy such that this is 0, isn't it. So, you can write like this. Okay. So, this is a good way of capturing what happens here, right. So, xy has to be orthogonal to x1, y1, xy also needs to be orthogonal to x2, y2. Okay. So, this is a nice way of writing it. So, this trick of writing it in terms of the points that you want and the equation that you want, if you go to 2 points, it will be like this. So, now everything depends on the rank of x1, y1, x2, y2. If this is actually linearly dependent, then you can have a line. If this is like all 0, then you will have the whole V. If it is linearly independent, then U perp will be 0. There is no non-zero xy which will be in the U perp. Okay. So, you see lots of interesting connections are getting established between equations and subspaces and all that and orthogonal complements. Already it is beginning to look interesting. So, you can see here this connections to null space here, all of that we will explore and sort of formalize in the next few slides. Okay. So, U equals V is another example. So, if U is equal to V, then U perp is just the 0, nothing else is there. Okay. Okay, so let's see a quick basic properties. If U is a subset of V, the first result is U perp is a subspace of V. Okay, so all the examples we saw before, you saw that whatever V was, the U was, U perp ended up being a subspace. Okay, so that's not too difficult to prove. I'll leave the proof as an exercise. You can check that the points of U perp are closed under linear combination. It's quite easy to see, right? So if any vector has to be orthogonal to all the points in U, if you take a linear combination, that's still going to be orthogonal to all the points in U. Okay, there's no problem there. And 0 perp is going to be V, V perp is going to be 0. Okay, and next is the interesting little result. The third point I think is very interesting. So U intersect U perp has to be either empty or it has to be 0. Okay, so so you can see why. So for instance, in some of the cases we saw U was x1 y1, and if x1 y1 is not 0 and U perp was a subspace, there can be no real intersection, right? So that point is maybe easy to see. If you see, if V belongs to U intersect U perp. Okay, so if U intersect U perp is empty, then there is nothing to do. Okay, if there is a V that belongs to it, then what should happen? Right, V belongs to U and V belongs to U perp also. So V should be orthogonal to V itself, which implies V is equal to 0. Okay, so if there is any vector in U intersect U perp, it has to be 0, or there could be no vector at all, in which case it will be empty. Okay, so this is the only two possibility for U intersect U perp. So particularly interesting case is, if U is a subspace, then U will have 0 also, and U intersect U perp will be 0. If U is not a subspace, then U should have 0, right? That's the only criteria. If U has 0, then U intersect U perp will be 0. If U does not have 0, then it will be empty. Okay, so that's a nice result to have. Another result which you can quickly show is if U is contained in W, if W is a superset of U, then the the orthogonal complement of W perp will contain U, right? See, if U is contained, something that belongs to W perp, right, will also be perpendicular to every point in U, right? So it should be contained in U perp. So the containment in the orthogonal complement will be reverse of the containment here. If U is a smaller set, U perp will be a larger set. Okay, so U is contained in W, U perp will contain W perp. Okay, so it will go reverse because the conditions are working that way. Okay, some basic properties, some basic intuition to build upon orthogonal complements. Okay, the next actual interesting case is when U becomes a subspace itself. Right, so far when we looked at, you kept U as a subset, we got some interesting properties. When U becomes a subspace itself, then it becomes much more interesting. Okay, so lots of interesting connections you can make between the subspaces that we know of and the complement. Okay, so let's say U is a subspace of Rn or Cn. I am taking a specific type of Fn, the usual coordinate vector space, to see what we can say. Okay, so in this case we will take an example where U is a span of these two. Right? This is how we specify subspaces, right? We specify the basis or a spanning set. Okay, here is a spanning set. So one could write this in terms of rows of a matrix A or columns. I mean, if you don't like rows, you can write columns as well. I am writing it as in rows. There's a specific reason why. Okay, so U becomes a row space of A, and A is this. Okay, so you can see this nice connection comes about. Any subspace I can do this, right? So what is U perp now? The set of all vectors in R4 such that the inner product of V and 1, 2, 3, 4 is 0. Inner product of V and 3, 4, 5, 6 is 0. This two you can combine just like I did before in the previous example and write it's the set of all V. So notice, see, remember, since U is a subspace, it's enough if I check orthogonality of V with the two spanning set vectors. If V is orthogonal to each of the spanning set vectors, then V will be orthogonal to any linear combination of them. So I don't have to go and check for orthogonality with every point of view. It's enough if you check for orthogonality with the spanning set of U. So that's a big simplification when U becomes a subspace. So U perp simply becomes just this definition, and this can be rewritten, right? So this inner product V comma this, you can write it as AV equals 0. So this is like a shorthand notation, and you quickly see the connection to the null space, right? So U perp, when U is the row space of A, is nothing but the null of A. Okay, so this is a good connection for Rn, right? So this is Rn. Okay, so this is in Rn. I should say that very clearly. This is for Rn. Okay, remember that. Now, if U is a subspace of Cn, where you expect complex numbers, and you write U as row space of A, so the problem in complex is, okay, so this is for Rn, where inner product xy is defined as x1 y1 plus xn yn. In complex, what are you going to do? In inner product will have this other definition, right? So x1 y1 bar plus xn yn bar. Okay, so this conjugate enters the picture here, right? So if you define A and make U as the row space of A, U perp in this case will become null of A bar. Okay, so what is A bar? You take conjugate of A. Okay, so instead of putting A, you have to put A bar. Okay, so what will happen now if you have A bar V equal to 0? Okay, so that is the same as A V bar equal to 0, and that will give you the inner product, right? So the proper inner product will come in, right? So in complex also there is a connection with the null space, except that you have to do a element wise conjugate. Okay, so we see that this complement and the 4 fundamental spaces of matrices are connected, and one can write it down, particularly for the real case. Real case is very easy, where you have the inner product, null of A is the row space of A perp, and you can also have for range, right? So you define the left null, and range will be the orthogonal complement of left null. Okay, so this is a good result to see. So we see this nice connection, and what you were doing when you found null space is actually finding the orthogonal complement of the row space. Okay, so this is very useful in some cases. So there are a few more results which are very interesting. Here is the first of them. So we know that if you have a subspace U, there is some W such that V becomes the direct sum of U and W. We know that that's true. Okay, so it turns out U perp is a candidate for W. Okay, so you have an inner product space V, you have a subspace U, you find U perp, then V becomes the direct sum of U and U perp. Why direct sum makes sense? We know already U intersect U perp has to be only 0, right? So that we know. So if I take a sum, it will become direct sum. That's okay. But then why should the direct sum be equal to V? That's the question, and this is a proof that you can write. It's a very easy argument. You start now with an orthonormal basis for U. That's where the starting point lies, not just basis, but an orthonormal basis for U, because we are in an inner product space. Any V now I can write in this fashion. Okay, so it's sort of like the orthogonal decomposition we saw before. You know, any V, now V need not be in U. If V were to be in U, then only this first part will come, second part won't come. So when it is general, I sort of do the first part, okay, and then write everything as V minus that. Okay, it's just V equals V written like this, right? So nothing major here going on. But interestingly, the first term ends up being in U, okay, and the second term ends up being in U perp. Okay, I'll ask you to prove this. It's not very hard. You can show for the second term, if you take a dot product of the second term with E1, for instance, what will happen? The first term will give you V comma E1. This term will give you minus V comma E1, right, when you're taking dot product with E1. And all the other guys will disappear, because they're all, it's an orthonormal basis, right. So you get V comma E1 minus V comma E1, and that will go to 0. Okay, so this is a bit interesting. This is sort of like an orthogonal decomposition of V with respect to U, and this is possible for any subspace U. So this part is very important and interesting. We'll come back to it in later lectures. This orthonormal basis is very powerful in this fashion. For any subspace, even if you have a vector outside the subspace, you can sort of write it as something that belongs to the subspace plus something that is orthogonal to the subspace. Okay, so you can sort of picture this. You have U, you have the whole V. If you have a V outside of that, you know, you can, there is something here, and then something that is perpendicular, right, and this is this guy, and this guy is in, right. So let me just write U perp like this. This is U perp, and this belongs to U perp. Okay, so any V that is true. So there is something that's here, something that's here, and this plus this would give you V. Okay. So you can write down a proof if you like. So this is very important to know. Okay. So and that's it. We are done, right? So any V can be written as something that belongs to U and something that belongs to U perp. So V is capital V is U plus U perp. Okay. So that's nice to know. So the orthogonal complement also has this powerful thing that it has a direct sum with U to give you the entire vector space. Okay. So if one can quickly write a corollary here. If V is finite dimensional, this result immediately tells you the dimension of U perp. It's simply dimension of V minus dimension of U. You could have also proved it using other methods, but anyway, so this is quite easy to see. Okay. There's another interesting result. If when U is a subspace, you take U perp, right? U perp will also be a subspace, right? If U is a subspace, even if U is a subset, U perp is a subspace, and then you can do a perp again. It turns out if U is a subspace, you will get back U. Okay, when you do complement twice, orthogonal complement of the orthogonal complement gets back to the original subspace. Okay, I'm not going to go through the proof. It's a bit technical. It's just showing two sets are equal. An element here is element there, except that you have to really watch out for what it means to say, perp of perp, and then look at it very carefully. It's the proof in your book is pretty nice. Please take a look at it. I'm not going to repeat it in this class, but this is interesting to know. Okay. So how do you find an orthonormal basis for U perp? Is there a easy method? Yeah, you can use extension, the orthonormal basis extension. You find an orthonormal basis for U, you extend to an orthonormal basis for V, and simply take the remaining guys. Okay, so it's easy enough to see. So this is quite straightforward to do. Or you find a simple basis for U perp and apply Gram-Schmidt. You could do that also. There's so many methods out there. So what is interesting because of these results is that you can specify U by either specifying the spanning set for U, as in give a basis for U, or you can give a basis for U perp. Both of these sort of determine each other, right? If you give a basis for U perp and you define a matrix with the basis is coming up one row after the other, what will be U? If you define U perp as a row space of something, U is simply the null space of that, right? So both of these are very valid definitions, and this is where the normal definition of a plane comes from, right? To specify a plane through the origin in R3, you can either specify the plane, vectors in the plane, or you specify just one vector orthogonal to it. It uniquely specifies the plane. Okay, so that's the idea behind these things. Okay, so this is quite powerful. You can use it depending on some problems. For some problems, specifying the spanning set is easy. For some problem, specifying a basis for U perp is easy. Okay, so for instance, if you want to test membership in a subspace, right? It's easy to check if it's orthogonal to U perp. I mean, the basis for U perp is better there, right? With the spanning set, you have to keep solving some equation or something, right? So it's not that easy. Okay, so I'll close this lecture with sums and intersections of some subspaces. We have done this before also. We looked at how to compute basis for the sum of two subspace, basis for the intersection of two subspaces, and one can also use these orthogonal complements and ideas from there to help us with this. Okay, so there are other ways of doing it, but orthogonal complements give you an interesting approach to this problem of sums and intersection of subspaces also, and it gives us some practice to think of orthogonal complements. Okay. Sum is easy with the spanning set. Okay, you have a basis for U, basis for W. If you want to look at U plus W, you already have a spanning set with you, right? Spanning set is U1 to UK, W1 to WK. You put them one below the other. You do elementary row operation, simplify. You find a basis, right? So you can find U plus W in a straightforward way. So what do you do for U intersection of U and W? One sort of textbook method, easy method, is this result. U plus W perp is actually U perp intersect W perp. Okay, so this result one can use to do intersection. So let me just first prove this result and then show you how this works. So proving this result, usually when you want to show two sets are the same, you want to show if some vector is in the left hand side, it's also on the right hand side, and some vector is in the right hand side, it's also on the left hand side. So if V belongs to U plus W perp, right? So remember U plus W, U is contained in U plus W, W is also contained in U plus W. So clearly, so if this belongs to U plus W perp, that same vector will belong to U perp and W perp. Okay, so it belongs in the right hand side. Okay, so this sort of shows, this shows LHS is a subset of RHS. Okay. So, the next step is to show RHS is a subset of LHS. So, for that let us define UPerp. UPerp is a set of all vectors V which are orthogonal to all the UIs, right. So, UIs are the basis for U, okay. They will be orthogonal to all the UIs. What is WPerp? Set of all V which are orthogonal to all the WI, okay. So, what is the intersection of these two? Set of all V which is orthogonal to all the UI and orthogonal to all the WI, okay. Is that all right? So, this is the definition. Now, what is that? That's at that point we are done, right. So, because UPerp is this, now so this is the same as the spanning set, okay. So, this is okay, V is orthogonal to spanning set of U plus W, okay. That is the definition, right. So, this guy becomes exactly U plus W perp, okay. So, any vector here belongs to U plus W perp. So, this sort of shows RHS is contained in LHS, okay. So, maybe even equal, you can see how this is true. So, this is a nice little result to have. So, if you want to do intersection of two subspaces, there is a connection between intersection and sums, okay. So, you can do a corollary here using the complement of complement idea. Instead of U, you put U perp, W, you put W perp. You see that U intersect W is U perp plus W perp, the whole perp, okay. So, this is a result one can use to find intersect. There are other methods also, I am just giving you a method based on orthogonal complement. So, this kind of connection is very interesting. So, let me show you a quick example of this and close this lecture, okay. So, here's two subspaces I have specified using spanning sets, right. So, U is row space of 1, 2, 3, 4, 3, 4, 5, 6 and W is row space of something else. Supposing you want to find U plus W, this is good enough, right. So, you want to find U plus W, it is nothing but all these 4 put one below the other, it is easy to do, right. So, maybe I should write that down. U plus W, the spanning set description is very good, it is simply row space of 1, 2, 3, 4, 3, 4, 5, 6, 1, 1, 1, 1, 1 minus 1, 1 minus 1. Okay, so that is easy enough to write. Now, U intersect W, what do you do for U intersect W? It is good to think in terms of the orthogonal complement. So, you find the basis for the orthogonal complement, which is nothing but this you have to do row elimination and find the null space of this. So, U simply becomes the null space of this guy. Okay, so once again, what did I do here? So, I found, so U is the row space of this, okay, and the U perp, right, what is U perp? U perp is going to be null of this itself, right. Maybe I am just going around in circles here, so let me not just write it, yeah, so this is not wrong, except that maybe you do not quite see it. So, U perp is basically null of 1, 2, 3, 4, 3, 4, 5, 6, okay, and you can find the basis of the null, okay. You do the the usual row elimination and find the basis of the null, you will find that to be 1 minus 2 1 0 and 2 minus 3 0 1, okay. So, there are other basis vectors as well, but this is the basis for the null, okay. This is the basis for the null space. So, U perp is nothing but the row space of this, right. So, U perp is the row space of 1 minus 2 1 0 and 2 minus 3 0 1. So, I can write U in other words as the null of this same matrix, right. So, it is all, I mean, I think in this one little thing I have specified so many connections. So, instead of writing U as the row space, I can write U as the null space of this guy. So, same thing with W, instead of writing it row space of this, I can write null space of this, okay. So, think about what I did here, right. So, I have U, I know U perp is null of that same matrix, I find the basis of the null. So, U perp becomes row space of this guy. So, now what will be U? U will be null of this same guy, that is what I wrote here, okay, same thing I did here, okay. So, hopefully you get this, this is a nice little connection that you can do here between row spaces, null spaces. So once you write U and W as null spaces of two things, U intersect W is very easy, right? U is everything orthogonal to the rows of this, W is everything orthogonal to the rows of this. So what is U intersect W? It needs to be orthogonal to all four of them. So you put one below the other, so you get null of this. And now you do row elimination here to get it into standard form. You get null space of this, and from there you can go back to the row space. Okay, so you find this is what is null of this. You have a basis 1 1 1 1. So U intersect W is row space of this. Is that okay? So these two row spaces have an intersection which is just 1 1 1 1. It's a dimension 1 intersection. Okay, so this kind of comfort in moving from spanning set to the orthogonal basis and orthogonal basis back to the spanning set can help you quite a bit in problems like this, finding intersection, finding some things, and this is very interesting to look at as well. Okay, so that's the end of this lecture. Thank you very much.